Okay, so hello everyone. Let's start off by just kind of going over, do you guys have any questions about the exam that you guys just took or the material that we went over this week? If not, we'll just kind of start at 4.5 and work our way through. Yeah, this week is, there's some content there. Is there anything in particular that you guys were having trouble with? Okay. I'll just start going. Okay, so we're starting with average cost. Thoughts on average cost, rate it. Okay, we will definitely talk about 4.8 then pretty extensively. Thoughts about average cost, guys. Rate it 1 out of 10. 10 being yeah, I totally get this, and 1 being what is going on. Yeah, okay, awesome. Perfect. Do you guys just want to move on to 4.6 then? Or do you want to do a couple problems from 4.5? Cool. All right. So let's take a look at question 3. So this is 4.5, and we are on page 206. So the graph of a cost function is given in the figure below. Part A is at Q is equal to 25, estimate the following quantities and represent your answers graphically. And B is estimating at what value Q is the average value of Q, or excuse me, the value of Q in which the average cost is minimized. So first thing to do is I'm just going to kind of sketch out the graph here. So this is going to be C of Q. And so this is Q, and we have, this is a little bit too extreme in terms of curves. So I'm going to redraw that so it works a little better. Okay. So there's Q. Here is 100, 200, 300. Okay. So this is all right. So basically what we're going to think about is, first, part A is we're thinking about at Q is equal to 25. So we're going to go through, and here is where Q is equal to 25. So this is that point. I'm just going to check to make sure in my book. Yeah, it's going to be approximately 200 is what the cost is going to be. So Q is equal to 25. C of Q is approximately equal to 200. That would give us an ordered pair of 25. So estimate the following quantities and represent your answers graphically. The average cost is going to be the slope from the, or a line, basically, you're going to draw a line from 0, 0 to the point on the graph. And that slope is going to be your average cost. So here's our point on the graph. We're going to start at 0, 0. We're going to draw a line going up there. and theoretically the sign would just kind of continue. And this is going to be, the slope is going to be rise over run delta y delta x, or in this case, 200 minus 0 over 25 minus 0. So it'll just end up being 200 over 25, or 8 over 1. So the slope, which is the average cost, is equal to $8 per unit. Are we good with this? Cool. Okay. So now we need to compare the relationship between the average cost and the marginal cost. And so do you guys remember what the marginal cost is? Okay, so like what is the marginal cost? Okay, so the marginal cost, if we remember, is just going to be the derivative of the cost, because we're looking at like the rate of change at a specific point in time of that cost. Okay, so we are going to be looking at, sorry, I'm just going to take a quick look at the book here. Okay, so well, hold on, give me a sec. I guess how would you guys like start this problem, like looking for the marginal cost? Because I can see a couple of ways to start doing this, and I'm wondering what method would be like the one that you're more comfortable with. Because we aren't given an equation for C. So the method that I would use is I would sketch a tangent line. And so like here's my point. My tangent line might look something like that. In addition, we know from this chapter that at a critical point on this graph, like a minimum or a maximum, there is going to be the marginal cost is equal to the average cost. And that's just kind of something that we got from page 205. They have the full proof on page 205. But the point is that this looks to me to be kind of like a minimum. So I'm going to say that the marginal cost is going to be like approximately equal to the average cost, because it seems to be very close to a minimum at least. And I would kind of use this like tangent line that I kind of sketched and say that it'll be, is this a greater slope or a lesser slope? So I'm going to say it's a little bit less. So I'm going to say that it's just under 8. Because we said that our average cost is equal to 8. So give me a sec. Whoop. Just want to make sure this is in line with what the book has to say. Okay, well, this is true. What would be the best way to do this? Perhaps maybe just drawing the tangent line. So it is less than 8. It is more less than 8 than I initially thought. So I think I'm just going to try to draw this tangent line as best I can. And then we're going to look at this graph and compare rise over run. Does that sound like something we can do? So this is going to be probably, let's see. So this is kind of, see, I'm not so hot at drawing tangent lines, and extending them to where they need to be is my issue. So I'm wondering what they exactly want us to do to like get a good estimate on this. Because it's not at a full minimum. Well, it's not at a minimum is the problem. So this is true, but this is not. So marginal cost is equal to average cost only at a critical point. And so this is not a critical point according to, yeah. So that's the issue that I'm running into. So I am going to, I totally should have looked at the back of the book beforehand. Okay. Okay, so what we're gonna do is we're gonna write down what we know. And so we know that at Q is equal to 25, C is equal to approximately 200. Let's take a look at 20. At 20, at Q is equal to 20. C is going to be approximately equal to what? What does that look like to you guys? 175? At Q is equal to 30. This is looking something like 210. So what I'm going to do is I'm going to kind of use my estimation skills. I'm going to find the average between these two things and see if that gets me a little bit closer. And if we need to get smaller, then we'll go smaller so that we can eventually find what the tangent line is here. So basically what we're doing is we're going all the way back to what we did at the beginning of the semester, and we're using average rate of change to estimate instantaneous rate of change. So we have delta y over delta x. Delta y is going to be equal to, this is equal to 30, and C is equal to, yeah, we're gonna try this and see how close it gets us to the right answer. But yeah, this is essentially using the same technique that we were using earlier in the semester, using average rate of change to estimate what the instantaneous rate of change is, because we don't have an equation that we can actually like take a derivative of. And my lines that I was trying to draw a tangent line of were just not precise enough. So it wouldn't have given us a fairly good answer. Okay, so that's kind of like something that you should like remember to do, I guess, as like you try to solve problems. If you hit a problem and you're like, not really sure what to do with this, good plan would be to like go back to what you know. Like, what do I know about marginal cost? I know it's the derivative. What do I know about derivatives? Well, it's related to average rate of change. It's related to the tangent line. What can I use to solve this problem? So delta y is going to be 210 minus 175. And delta x is going to be 30 minus 20. So this is going to be 2535 over 10, or 3.5. Yeah, that's about reasonable. The book says that the marginal cost is equal to 4. So if we were to edit our line here, we could be able to get more. We would be able to get more precise. We'd be able to say, like for instance, if we do from 25 maybe to 20, then it would find this area here. But we just kind of like close in on the point. So let's try that. Delta y over delta x. Nope. This is 200 minus 175 over 25 minus 20. So this would end up being 25 over 5. So this is going to be equal to 5. So this is a little high, and this is a little low. But basically, we're just estimating. So 4 is a pretty reasonable estimate to make here. Are you guys feeling cool with the way that I just approached this problem? Because if you're confused, like, let me know. Okay, so that's how I would approach kind of like estimating the marginal cost. Okay. Yes. If given a formula, definitely just take the derivative. It's so much easier. Yeah, usually you are given some sort of a formula and you're not just told to like here's a graph, just kind of work with it. No formula or nothing. So yeah, just like default to what you know about derivatives. And it should work out because what you know is true. Awesome. Okay, that's good. That's good. Okay, so then we are going to estimate at what value Q is at what value of Q that average cost is minimized. So what does that mean? Hang on, right up here. So here we say average cost at 25 is equal to 8. And then we say marginal cost at 25 is equal to, looks like 28, sorry, it's equal to 4-ish. So that's what we just got from our little experience through the graph. And then we are estimating at what value of Q the average cost is minimized. What does that mean? What do you think a minimized average cost is going to look like? Can the average cost ever equal 0? It's not going to be able to because this is like the average cost of an item. So the only way the average cost is equal 0 if so is that Q, the cost of the item, is equal to 0. So something would have to be free if that were the case. Okay, so what we're looking for is not necessarily the change in the graph takes place. Well, what we're looking for is the smallest slope of the average cost line. So we're looking to minimize slope. So for instance, if we were to take this point, this would be our average cost line, correct? If we were to take this point, our average cost line would kind of go like this. If we were to take this point, it would be a little bit different. So all of those are kind of examples of, like, if we were to take an average cost line, what's going on? Sorry, that was bad. I had to make all of this in dots. Okay, so where we're trying to find the lowest slope, the smallest slope, is going to be, where did it go? It is going to be where the line is like tangent to the curve. So where marginal cost is equal to average cost. How? Yes, exactly. So this is how I kind of got to this statement. I said that average cost is going to be tangent to curve. This is equal to being derivative. Tangent to the curve, this is equal to being marginal cost. So the average cost is going to be equal to the marginal cost. Where is that the case? We were just talking about this. It's going to be at the critical points. Oop, where did my pen go? So that would be the maximums and the minimums, or just the other critical points, I guess, because there are critical points that are not maximums or minimums. So let's say that's about like right here-ish where this critical point is. I believe that should be correct. Check. Oh. So I estimated about 20 units because I'm looking for the critical point. What I did wrong was I had this graph really obscured, and I was looking at the graph that I had drawn and not the graph in the book. So my graph is not as good as the graph in the book in terms of what exactly is going on, so I would highly recommend you look at the graph in the book. The graph in the book is going to have let's see. So I marked out an inflection point. They're saying it's going to be at about 30, which doesn't appear to be a minimum to me. So I wonder what they're doing. Oh, darn it. Oh, darn it. Ah. Function, are they equal? That makes sense. All of this makes sense. I guess we're just gonna figure out what's going on here. Okay. Jeez Louise, this was supposed to be an easy problem. Okay. Do we understand that we are looking for the place where the marginal cost is equal to the average cost? Like, is that clear? At least. Cool. Okay. We know that that happens at critical points. What we're having the issue with is that the book says it's at 30, and I'm having a tough time believing it, but we're going to test it out. So the average cost at 30 is going to be, we know it's somewhere in this region, right? We can establish that. You guys cool with that idea? Yeah, because if it's like up here, then that's a very high slope. If it's like over here, that's a little too high. But if it's like going to here, it's going to be pretty tall too. So we're looking for a smaller slope, so it's probably going to be in this lower region here that I have boxed. Okay, so at Q is equal to 30. C of Q, according to the graph, is equal to, what did we say, 210? Okay, so our average cost is going to be 210 over 30. This is minus 0 and this is minus 0. So this is going to end up being $7 per unit. So it's going to be, cross out those zeros, 21 divided by 3. Okay, so we know that the slope at this point is 7, and we know the slope going to here at 25 is equal to 8. So we know that this slope is less. So let's try out now going to 35. 35 is going to be about right here. So we draw a line from there to there. We say Q is equal to 35. C of Q is equal to 250, 260. What do you guys think? Let's go 260. Oh, 250. There we go. So then we have 250 divided by 35. So calculator. This is going to be 7.14. So 7.14 is greater than 7. So basically what I did here is I established some boundaries. Looking at the graph, doing some like light sketching, I said like maybe it can be at like where could this like point possibly be? Maybe it could be like in this area. So I estimated what it would be at 30. I estimated what the average cost would be at 25. I did that earlier. I know that because it's in this area, and I know that 25 is greater, then it's probably going to be, and 35 is greater, I know it's going to be between 25 and 35. So I like 30 is like a reasonable estimate for this at this point. Then basically what I'm going to do is try to check my answer by finding out what the marginal cost is. Because I know that my marginal cost is going to be equal to my average cost. So at 30, let's do 25 to 35. I'm going to do 250 minus 210, 35 minus 25. This is going to be 30 over 10. This is going to be 3. That does not seem right. What's going on here? Okay. Something is going very wrong. I'm so sorry. I am so sorry, guys.
Olivia,
Oh,
isn't that 40/10?
Yeah, it is. Clearly, I have no idea how to do math, so. Okay. It's still not quite what we need, though, because we're looking for a marginal cost that is equal to our average cost, right? Okay. Well, if you guys have any suggestions, please let me know, because I thought I knew how to do this problem, and I guess I don't. So that's kind of frustrating, and not very helpful for you guys. So we're going to take a quick sec. Maybe the book is wrong. I guess that's a possibility. I'm going to put myself on mute for like 2 minutes and do some reading. And I encourage you to do the same. And can we reconvene in a couple minutes and figure out what's up? Awesome. Okay. So sorry about this, guys. Okay. So. Oh, I better start. Okay. Is everybody back? Cool. So basically, do you see this chunk here that I did? What I did earlier is I was doing this average, not from there. That's not what I was doing. I was doing the average cost from here to here in an effort to estimate marginal cost. But what I was doing was a poor estimation because I had such a large range and because there was such a big change going on here. If we were to like zoom in on this area, the graph kind of looked like this, and I was just kind of very generically doing that. And that was not really giving what I needed because I had a steeper slope there. So what I did is I brought in my edges to give a better estimate of what was going on. I said instead of doing 25 and 35, I'm going to do 29 and 31 and estimate what that is. And this is going to give me a better estimate. Okay. And then this is kind of what I did. I said this was approximately 205, approximately 220, approximately 7.5. Again, all of this is estimates, but the marginal cost at 30 is approximately equal to the average cost at 30. So we can assume that that is all right. I am going to do a little bit more looking into doing average cost and marginal cost without a function explicitly given, if you're just given a graph instead of a function. And I might make like a supplementary video or something, but for now I think we better move on to some other stuff. This stuff is theoretically quite easy to do if you have a function that is given to you, but since this problem was just working with this graph, it made it a lot harder. So, are there any questions about what's going on here? Okay, let's just move on. We're gonna do number 5 from this section just to prove that we can do it. And then we're gonna move on to section 4.6, okay? So question 5, we have the cost function C of Q is equal to 1,000 plus 20 Q. So use that to find the marginal cost to produce the 200th unit and the average cost of producing 200 units. Okay, so basically, we know that marginal cost is equal to the derivative of C of Q. So what is the marginal cost equation going to be? Exactly. So marginal cost always equals 20. So it doesn't matter that they're asking us to find the marginal cost of the 200th unit. They could be asking us to find the marginal cost of the first unit or the 550th, but it's always going to be 20, so the marginal cost is going to equal 20. Cool. Then we're going to do the average cost. So we know that Q is equal to 200. And we know that C of Q is going to be equal to, this is C of 200. This is 1,000 plus 20 times 200. So this is 1,000 plus 1,000. It's going to be 5,000. Awesome. So what we're going to do is we're basically going to find the slope from the point 200. We don't need to entirely have a graph here because we know that our function goes through this point and we need to find a line that goes through this point and 0, 0. So what we're going to do is delta y over delta x. So 5,000 minus 0 over 200 minus 0, or I'm going to cross out these zeros, that's 0. 50 divided by 2, 25. So the average cost is equal to 25. Let's see what Q, excuse me, is equal to 2. Make sense? Awesome. Okay, let's move on. I will get back to you on what to do if there is just a graph and no equation. So, elasticity of demand. Thoughts on this? Good, bad, in between. Is that a 6 out of 7 or a 6 or 7? Okay. Yeah, so basically, this is just going to be considering the sensitivity of demands. How does increasing the price of an item change the amount of goods that are demanded by, so basically this is considering the fluctuations between the supply and demand, and it's represented by a number called the elasticity of demand. So let's do problem 1. The elasticity of a good is E is equal to 0.5. What is the effect on the quantity of the quantity demanded if there is a 3% price increase and B, a 3% price decrease? So I'm going to start by going back and looking at my equations that are given for this section. We have the elasticity of demand is approximately equal to the absolute value of delta Q over delta P over P. So what are these Q's and P's? This chunk here is percent change. Q over Q is percent change in quantity. And then this is percent change price. So it's handy that we have this in terms of like percent changes. So so basically what they're saying is this equation also can be expanded. You can have E is equal to P over Q times dQ dP. And so this is basically more precise. But the general idea is E is equal to percent change Q over percent change P. So we know that from all of these equations. Let's just kind of put things in the equation. Sorry, let me erase all of this. Okay. So a 3% price increase. We have E is equal to 0.5, which is equal to percent change Q over percent change P. Trying to think the best way to like write this. Are you guys okay with me using deltas as like change, even when it's with a percentage here? Cool. Okay. So we're just talking about the percentage change. The quantity, the elasticity is not going to change. This is constant. But this is going to change. This is constant. This will change with P so that this maintains being constant. So basically, I'm going to set up an equation that compares these two. I'm going to say, so I'm going to put this in a way that allows me to so this is going to be 1 and 1, P1 plus 3. So I'm just going to simplify these to Q1, P1, Q2, and P1 plus 3. Is that okay? Okay, so then my equation is going to look like this. I'm going to multiply both sides. Q plus 3. 1. Kind of blowing through the algebra here, but it's going to end up being P1 Q1 plus 3 Q1 is equal to Q2 P1. Actually, I don't think I want to distribute it out like that. Why would I do that? Trying to make things simple, not make them more complicated. So, what we're trying to do is find out what the relationship is between Q1 and Q2. So I shouldn't have moved this P1 over here. I'm going to divide everything again by P1. Okay. I just kind of like simplified these. I said that we aren't given more and one here. Okay. So the way that I kind of set up this equation is a comparison. I said that I know that there is some number that the percent, because we know that, okay, so we know that E is going to be the percent change in Q, and we know that over the percent change in P, right? That's what this equation is telling us. Okay, so what I did up here was I said, okay, so I know I have some percent change in Q, and I'm just going to name that variable Q1 because I don't want to write percent change Q or percent delta Q1 every time to like represent that. So this was my shorthand way of saying, okay, so my percent change of Q is going to be percent change Q1. And the reason I labeled them Q1, P1, and Q2 and P2 here is because I had before price increase, and then I had after price increase. So I'm trying to, I know that E doesn't change. And so I know that these two ratios are going to equal each other. So I know that the percent of change in quantity before over the percent change in price before is equal to that after. Right? Are you following me up to here? Yes, no, maybe so. Okay. So then I know that this percent change P after is given to me as part of the problem. There's a 3% price increase. So percent change P after is equal to percent change P before plus 3%, right? And then because I didn't want to write all of this every time, I did some algebra. What I did is I said, this is Q1 and this is P1. And I just used these variables as kind of stand-ins for this whole phrase. And I'm going to put the whole phrase back by the time I get to the end of the problem so that I can like look at it better. But because I wanted to simplify the way that I was approaching like the algebra of it. So what I'm looking for in this problem is going to be Q after, or what I called Q2, because I want the percent change in Q that occurs when there is a percent change in P, because the ratio is always going to be equal to 0.5, the ratio of the two. So I'm going to try to figure out what has to change in Q in order to change in P. Are you following this? Okay. So what I am going to go back to doing is I'm over here. I'm dividing everything by P1. I am, sorry, I'm running in green. Okay. So, Q2 is going to be equal to, I guess I am going to multiply this out. So it'll be P1 Q1 plus P3 Q1 over, all of this is over P1. Okay. So I'm going to eliminate that. And let me move this. Okay. I never use this side of the board because this is usually where my chat box is. So I'm going to go all the way over here. This chat box is still open, by the way, so I can still see what you guys are saying. And I'm going to say that Q2 is equal to Q1 plus 3Q1 over P1. Okay? Is everybody okay with what just happened algebraically there? I'm not getting any responses. Okay. So then I'm going to change these back into percent change. Q2, this is what I want, is equal to percent change Q1 plus 3 times, and then I know that percent change Q1 over percent change P1, this is before, this is going to be equal to E or 0.5, right? So I'm going to take this. I know that this phrase is equal to this. So I'm going to put that right there. 0.5. And then I'm just going to bring this down here. So percent change Q2 is equal to percent change Q1 plus 1.5. Or, this is our answer. So if the price, I'm gonna, well, I don't know where to put anything. Okay, so if price goes up by 3%, then quantity, in this case, is gonna go up by 1.5, or the percent change in quantity is going to go up by 1.5. Which is what the question was asking. So what is the effect on the quantity demanded of a 3% price increase and a 3% price decrease? So part A is this price increase, and we're saying that the percent change is going to rise after the price increase. What are your thoughts on what's going on here?
For a while, I was I was getting lost because
Okay.
it was moving from one side to the other. Like
I'm sorry.
I do get what you eventually got at the end, but
Okay.
is there another way to do it without going through all the many steps?
That is a good question. Okay. I guess this is just kind of like what made the most sense to me is to compare the ratios. So that's how I approach the problem. Let me take a sec. Yeah, there really is. Sorry, I was just reading through the book again, and they have an equation that really kind of relates these two things. she laid it out, equal to change in Q over Q. Yeah, I think Kasha is probably, she probably did a better job of laying it out than me. Sorry about that, guys. Okay, so let's, basically, one way of looking at this is delta Q over Q is equal to, or approximately equal to, negative E delta P over P. So this is another like way of like thinking about the equation. E is approximately equal to delta Q over Q over delta P over P. We just like moved this around. So what this is saying is that if quantity or if price increases, then quantity is going to decrease, which makes reasonable sense, like the quantity of goods demanded. So this is percent change price. This is percent change quantity. So percent change quantity is equal to negative E percent change price. So this E is going to be equal to and so the percent change is going to go up by 3, and the percent change quantity is what we want. So the percent change quantity, I don't know why I didn't do this first. I'm so sorry, guys. I just wasted a lot of time. But the quantity of goods demanded is going to go down by 5%. So basically, what we've learned from this is that I have a tendency to overcomplicate things, and I missed a negative sign when I was solving it. This makes more sense in terms of how to solve and answer. Thoughts, comments, concerns?
This way is much more understanding.
Yeah.
Simpler, much simpler than before. I was getting it, but it was very hard to continuously follow all those changes.
Yeah, I'm sorry. Yeah. I mean, I still think it's important to consider it as like a change in like the ratio of the two, but this is just a better way to visualize it in terms of actually solving a problem.
Okay.
So, Kasha's right. So for 1B, if there's a 3% price decrease, then this is just going to be delta Q over Q. This is the percent change. It's going to be equal to negative 0.5 times negative 3, or delta Q over Q is, excuse me, equal to 1.5%. So the quantity will go up. The quantity sold will kind of go up. Okay. I am so sorry that I made that way too complicated. Wow. I maybe should have not done that. Okay. So, do we want to talk about logistic growth now? I actually do know what's going on with this, like, fairly. I mean, like, not. I get logistic growth. Logistic growth makes like so much sense to me. Logistic growth and surge growth are like my thing.
Before like we move on, like, I do get the elasticity one, but they're when they word them, I'm having like trouble with that. Like when they say like, all right, E equals 1, what does this tell you about the change? I had written down a question. I need to find it.
Oh, yeah.
From the test. And I thought from what I read in the book that I had it right, but then it was saying something totally different.
Okay, is this from the quiz?
From the quiz, yeah.
Okay. I don't know if I'll be allowed to solve the quiz question.
No. No, I'm just saying, I wasn't, yeah. Yeah, so like the relationship part of it, like where it's telling you like if E1 is less than 1, the demand is elastic and the revenue is increasing. Like I was getting a bit confused on the quiz with those, because what I thought was not what the actual answer was. But I'll send it to you separately.
Yeah, please do, and I'll get back to you on that. For sure. Okay. So let's talk about logistic growth, which is, sorry, I'm a biologist, and so I study like biochemistry, and so like logistic growth and like surge growth, all of this is just like very important to what I study. So it's like my favorite stuff, which is, I get very excited about it. Okay, so we have the logistic function, and it is going to look like this. It's equal to slash f of t is equal to L1 plus CE to the negative KT. Okay, so there's a lot of like relationships to like consider, like what's going on with this function, but basically kind of looks like this, right? And so it's going to kind of plateau off where it's not going to get any larger. And so this is just like very generic. This is like what a logistic function looks like. So if you see something that looks like this, start thinking, maybe I should use these equations. This equation. Okay. So let's take a look at some of the problems. Okay, so let's start with problem 1. If T is in years since 1990, one model for the population of the world, P in billions, is P is equal to 40 over 1 plus 11e to the negative 0.08 t. Okay, so they are going to use logistic function a lot for like population, because it kind of like has like a carrying capacity like built into the equation. So A, what does this model predict for the maximum sustainable population of the world? AKA, what is the carrying capacity? So when they're talking about like this maximum sustainable population, they're asking like, what is this value right here, where it's not going to go above that, and if it does, it's just going to go below again, because that's just how this function works. It's not going to go above that line. That is going to be equal to the limiting value for L. So basically what happens in this function, we have some constants. We have K, which is constant, we have L, which is constant, we have C, which is constant. The only variable we have is this time thing, okay? And so basically what's gonna happen is that one way I really like to think about this function is that we have P is equal to, and then I'm gonna do minus a big number. So this is where T is large, and then compare it to a small number. Okay, So this is where t is small. And so this is kind of like a general case that I hope will kind of like help you guys understand like what's going on with this function a little bit better. So generally speaking, if t is small, what does that say about e to the negative like small number? Well, we know that, let me switch colors so that it's a little bit more beautiful. Okay, so we know that if we have e to, let's say, the 2, that's going to be e times e. But if we have e to the negative 2, it's going to be 1 over e times e. So that's going to get very small. How would e to the negative 1 compare? So e to the negative 2. There we have 1 over e, correct? Or e to the 1. So this is larger than e to the negative 2, correct? Okay. I hope you guys are following me. You're not putting anything in the chat box, so I'm not entirely sure, but I'm gonna trust you guys are following me unless you put something in there that explicitly tells me to stop. Cool. So this trend kind of continues. For instance, if I took e to the negative 102, this is going to be smaller, a smaller number than e to the negative 2. So this trend kind of continues. So if I have e to the negative small number, then this is going to be equal to 1 plus c e, or 1 plus some 1 over e to this number, okay? I'll over that. What we're really considering right now is this value, c times e to the negative number. I'm going to do some erasing really fast. Give me a sec. This is going to be the same process that we're going to go through for this one. So this is going to be a large number. So CE to the negative large number. So what we're going to do is we're going to compare the two. We have L over 1 plus C times 1 over E to a big number. Compared to L over 1 plus C 1 over E to a small number. Which is going to be bigger? Or rather, which term, C times E to the negative number, is going to be bigger? Well, this is going to, is somehow not a pen. What on earth is that? Okay. So this is going to be L over 1 plus C divided by E to the big number. So here, C over E gets very small. So as t goes to infinity, C over E to the t goes to 0, correct? In terms of like limits. Actually, I'm going to make this explicitly written in the limit format, so that maybe it's a little bit easier to see. Okay. So if I have limit of C e to the negative t t goes to infinity, this is equal to 0. So this gets very small. This also gets small, but it is less small. So then we're going to compare, okay, which one of these is going to have the larger value. Here we have L divided by 1 plus either a very, very small number or a kind of small number. Basically what this is eventually getting to is that if t is tiny, if t is small, then 1 plus c e to the negative t is going to be larger than if t was big, which means that L is going to be, or P is going to be this L divided by this larger number. If t is going to go to infinity, like this limit kind of implies, and c e to the t is going to equal 0, let's take a look at what would happen in this case. We have P is equal to L over 1 plus, we're gonna say T is going to infinity. So this is gonna be 1 plus 0. So this is just gonna equal L over 1 or L. So our carrying capacity is literally just L. So the way that this function works is to, over time, it's going to approach L, but it will never get larger than L because this number can never be larger than 1. Thoughts on this? This is kind of an important conceptual part of understanding how this equation works, because basically it's a comparison between okay, so if I have a tiny number here, if I'm looking at right here, I have L divided by a bigger number, versus if I'm looking over here, I have L divided by 1. And so L divided by some number is going to be less than L divided by 1, if this is just L. This is positive integer. Okay. Are we all okay with this? That is I think the more important takeaway from this section. Okay. So going back to problem 1, what does this model predict for the maximum sustainable population of the world? Well, we're basically going to ask, as time goes to infinity, what does P do? Do isn't spelled with an E. So as time goes to infinity, P is going to approach 40 over 1, or P is going to approach 40. And this is in terms of billions. So in this model, the population will reach a carrying capacity of 40 billion people. Okay, so we're not going to graph P against T, but very explicitly, but it's going to look something like this, and this is going to be 40 billion. Okay? You've got this, and then it flattens out. So according to this model, when will the Earth's population reach 20 billion? So part C is going to have us work with this model to determine when the population is going to be 20 billion, which is going to be half of the carrying capacity, correct? So there are 2 ways we could solve this. We could do this the long algebraic way of saying P is equal to 20 is equal to 40 over 1 plus 11 e to the negative 0 t. And solving for t, but I believe this is the point of diminishing returns. Is there an easier way to solve for this? Perhaps not. No, I think that might just be the easiest way. Although, we could, is the inflection point. So, the other thing we could do is find P double prime, find critical point, inflection. But that is just going to be where P is equal to L over 2. And I'm not sure if that's going to give us exactly what we want in terms of like what the time is going to be, because this is time versus population. So I would initially just start off using this. This is kind of similar to when we had like doubling times and stuff like that with our exponential functions, what we would do. But we could also take some derivatives and try to solve it using that method, but I'm not entirely sure if that's a dead end or not. That's not how I have ever solved a problem like this. So if you guys don't mind, I'm probably just going to solve it the way that I know how. Is this how you guys would solve it? How you guys would approach the problem? Like, how would you guys approach the problem if you saw if you saw a problem that was asking for? Yeah. Okay. So that's how I would do it too. Okay. So there's just going to be a lot of algebra here, so I'm just going to kind of algebra dump it all in one go. If you see a mistake, please call me out, because we all know I can make a lot of mistakes. So 20 times t 40 divided by 20, 20. So 1 plus 11 e t is equal to 2 minus 1 minus 1, 11. E to the negative 0, 8 t is equal to 1 over 11. So I'm going to take the natural log of both sides. The natural log of 1 over 11 is equal to negative 0.08 t. This is going to be equal to the natural log of 1 minus the natural log of 11, right? The natural log of 1 is going to be 0. So we have negative natural log 11. No. No. What did I do? Did I mess up my natural log rules?
I didn't do it that way. I just, well, I don't know if it can be done that way either, but I took the natural log of 1 over 11 and then divide that by
Yeah.
that. I don't know if it will give you the same answer, but
yeah. Here, let me put it. Like, I think that natural log rule should be a-okay. Okay. But where did my calculator go? So basically, the question is the natural log of 1 divided by 11 the same So the natural log of 1 divided by 11 is negative 2.397. And the natural log of negative 11, or the negative natural log of 11 is going to be negative 2.397. So they're the same thing, same answer. This is just kind of using the natural log rules. But you can solve it just as easily if you have a calculator using that. They would probably want you to simplify it on a test. Like if there was an answer, they probably wouldn't say it's the natural log of 1 over 11. They would say the negative natural log of 11, but it all like works out. So this is going to end up being 29.97. Yes, it is. I mean, yeah, it works both ways. You were also right. I want to establish that. So the way that what this problem is asking for is what year will the Earth's population reach 20 billion? And that is going to be 1990 plus 29.97. Or basically, according to this model, let me move this chat box. So it's saying 30 years down the line, because our starting year t equals 0 is going to be 1990, this is what the population is going to be. Is the population of the Earth 20 billion people approximately now? No. We could also use this model to figure out what they thought the population of the Earth would be in 2018, but it is probably not going to be very accurate because this doesn't seem to be like an incredibly accurate long-term proposal. Cool. Okay. So that's the method that you would go through to find what the population is at a certain point. So it is the same technique as finding W time, etc. So you basically just do the exact same thing you would do with an exponential function, but do it with the logistic growth function. Thoughts, comments, concerns, questions? Maybe, maybe not. Okay, so we had some specific questions about the surge function. Right? So we're going to finish up by talking about the surge function. Also, very valuable in biology. You see a lot of the times they'll talk about like concentrations in the bloodstream. Just a very generally useful thing. Okay. So this is 4.8. Okay. So the function is going to be y. That's really ugly. Y. Wow. Y is equal to ATE to the negative BT. Now, how does this differ from the logistic function? Like what stands out to you as going to be different from a logistic function? For me, when I look at this function in comparison to the logistic function, I see that there are two terms. So if t changes, there are two different ways that we have to consider it. Like if t gets larger, then the term a times t is going to get larger, but the term e to the negative bt is going to get smaller. So it's going to be a little bit harder for me to make like the same like general statements. Like if b gets big, or if t gets big, what's going to happen? Because I could just say in the last one that if t gets big, then we're going to approach L. But in this case, that's not necessarily going to be as easy to do, because there are two different iterations of t in the same function that both play a very important role. Other important like things to note, 1/2 of B is going to be the time of peak concentration. And then are there any other, no, I think that's generally it, like in terms of like what you can know about this. Also, you're going to want to know in terms of like terminology, there's a minimum effective concentration. So like they would draw a graph that kind of looks like this. So you have a peak, looks like this. If this is the minimum effective concentration, then we have a very small time span in which this drug is going to be working. But if this is the minimum effective concentration, we have a much larger time span where the drug is going to be working. So is everybody cool with all that I kind of just laid out? Cool. Okay. So let's start with number 1. If time t is in hours and concentration C is in nanograms per milliliter, the drug concentration curve for a drug is given by C is equal to 12.4 T E to the negative 0.2 T. Graph this curve. We're not going to do that because like it is important that you be able to graph this, but generally speaking, you know what this is going to look like, and like me graphing it using this pen and this tablet is not going to be very pretty. So how many hours does it take for the drug to reach its peak concentration? Well, if we look at part B, we know that peak concentration is going to be equal to time 1 over B. So B is equal to 0.2. So 1 over 0.2 is going to be equal to the time of peak concentration. And so the way that I kind of most easily do this is I say this is equal to 2/10. So I just do the reciprocal. I say this is going to be 10 over 2 or 5. So the time of peak concentration is going to be, this is T in hours, so this is going to be 5 hours. In. Are we all okay with part B? Awesome. Okay. So if the minimum effective concentration is 10 nanograms per milliliter, during what time period is the drug effective? So we're saying the effective concentration is going to be equal to 10 nanograms per milliliter, and so we're going to try to find a time period. So what I would do is solve or add, wait. Okay, so basically what I would say is that the concentration is going to be equal to 10, and this is going to be equal to 12.4 T e to the negative 0.2 T. So I'm going to start by just dividing this by 12.4. So this is going to be, get your calculator out. It's going to be 0.806 is equal to T e to the negative 0.2 T. Then I'm going to take the natural log. So take the natural log of this, and it's the natural log of 8.06. So this is just like a term. And so this is going to be the natural log of T times e to the negative 0.2 T. So what we can do is use our natural log rules to say that this is actually equal to the natural log of T plus the natural log of e times e to the 0.2 T. And use our natural log rules again to say this is natural log T minus 0.2 T. Correct? So this function is not as happily solvable as I kind of wanted it to be, but that's fine. So basically what I'm going to do is try to facilitate, I'm going to move around some logarithms, try to make it prettier. So instead of moving over this, I'm going to say that it's going to be minus natural log T is equal to negative 0.2 T. Is everybody okay with what I've done here? I just brought over this natural log T from one side to the other. Okay, so natural log minus a natural log is actually going to be equal to the natural log of 0.806 over T. Correct? So it's going to be equal to the natural log of that term. Trying to, oh gosh. What I need to do is combine these T terms. Oh, darn it. Algebra, don't fail me now. Sorry, I took like a whole class on like logistic functions last semester, but like we did not cover search functions as much as we probably should. So what are your guys' thoughts? So I clearly hit a brick wall trying to solve it my way. Are there other ways that we can think about solving it that would perhaps be a less algebra intensive and better method of solving?
I got lost trying to solve it, to be honest. So,
Like doing what I was doing up here.
yeah, like
Okay.
before when I was trying it, like I had the hardest time, especially that it has the two different T terms in it. I was
Yeah.
trying to figure out how to just get them all in one side, and I figured that was probably difficult.
Yeah, getting it into like an equation, like to solve it the way that I was originally going to solve it, is kind of unreasonable now that I'm like looking at it. If we're looking in the book, in example 3, they're having us use a graph, which is something that we were told to do at the beginning of this like problem, but did not do because it was going to be really time intensive. But it would just be very easy to tell what it would be given a graph. You guys, like if you look at the graph, should be able to tell if our minimum effective concentration was 10. What time period the drug would have been effective. So I guess the question is, do you guys want to draw this graph so that we could get a better idea of what's going on? Because in order to solve this, I think we need to draw the graph. Okay, so the way we're going to do this is I'm going to enlist your help to get some calculators going, and we're going to just brute force. We're going to do some points, figure out what's going on. So we're going to find C of 0, C of 1, C of 2, C of 3, C of 4, like all the way down, okay? So when you put one of those in the calculator, just let me know, put it in the chat box what the answer is going to be for one of those.
Olivia, I just looked it up from the discussion board, and even Professor Stan, he didn't explicitly solve for T. He used the graph.
Yeah, that's
because he said it was hard to like just solve for it. So
yeah, going through all of that is like see, this is kind of for me, when I look at a problem, I like try to solve it one way, and if I hit a brick wall, I don't like want to beat a dead horse. So I hit a brick wall. I couldn't like go any further solving for T that direction. So using the graph is going to be the best way to solve the problem and to like figure out actually what's going on. Okay. So we know that our peak is going to be at 5. So I hope going up to 20 is going to make it okay. So C of 0 is going to be equal to 0. C of 1 is going to be equal to, like I said, like if you're putting this stuff in the calculator, please put it in the chat box so that like we can just get this graphing stuff done with a little bit faster. Okay, so 1 is going to be 10. Okay, so Casey is saying in the chat that basically, this is going to be over here. 14 is going to be at 10, and 1 is going to be at 10. So what this graph is going to kind of look like is like this. Is that about right? So I'm going to go through myself. So yeah, moral of the story, if you try to solve for t and it doesn't work, then just don't push it, just use the graph. So our minimum effective concentration is at 10. So if the minimum effective concentration is 10, during what time period is the drug active? The drug is active between hours 1 and 14. So complications can arise when the level of the drug is above 4 nanograms per milliliter. How long must a patient wait before being safe from complications? Well, this is, I just kind of drew the line at 5 instead of 4. So we're looking for where it is below 4. So 20, C of 20 is equal to 4.5. So it's going to be after C of 20. If you were to continue looking at the graph, C of 21, or let's do C of 22. It's going to be C of 22 is going to be 3.349, and C of 21 is going to be, so it's going to be between 20 and 22 hours. So now instead we have to figure out what 21 is so that we can narrow this time span down a little bit more. So this is 3.9. So it is going to be, there are going to be dangers of complications. Between hours 1.5 or 0.5, excuse me, and 21. So that's a lot of time for complications. And during all that time, it is perhaps not active. There are periods of time where the drug is not active, but the possibility of complications still exists. Okay. Thoughts, comments, and concerns? Feel free to just say whatever you'd like in the chat. So did they do this problem like on the discussion board? Oh shoot, okay. I should probably check that beforehand next time. Sorry, I usually try not to do the same problems that you guys are already doing in class. So next week I will do better and make sure that the problems I do are not on your list of things to do, so that maybe you can get some different exposures. If you don't have any questions, we've been at this for about 2 hours now. So I'm probably gonna get ready to sign off if that's okay with you guys. Awesome. Email me if there are any issues, because like I said, there's some things going on in this that may like cause some problems, and the language can be really tough. So again, I'm sorry that I messed up that problem with the average cost. and I will get back to you on how best to do the graphing, but not with an equation for the average cost stuff. Cool. Okay.